Today, I put together a group of problems that involve torque and angular acceleration without rolling. Nearly all of the problems I had with this material involved some rolling because I usually introduced it about the same time. Free body diagram for the rightmost mass on this thing. It's going to have its weight, and then it'll be the tension on the right side that is acting on it. And I may have another unknown here. The tension on the left side will be zero in this case because I've got friction acting between the cord and the other thing. So it won't be quite as simple as the other one. I'll also have on the left side, I'll have M sub L G. This is the free body diagram on that side. I'll have T sub L acting on it. And we'll just have to see what we can do with this thing. Now, before we never had to deal with the disc that we were thinking about there. This time we do, and I'm just going to draw a little circle for it here. I just bonked the camera. Lights. Okay, so now we've got this thing, and I'm going to take and just apply the tension on the right. Actually, if I treat the tension on the left a little different, maybe we'll see what happens with this. So tension on the left, tension on the right. Let's see. I'm going to ignore the support force of the that's supporting the weight of the pulley. It actually balances the weight. It's the torques that are produced on the outside that will tend to cause rotation in this case. And so we'll just have to see what happens with this. Okay. For the rightmost mass, I'm going to let downward be positive. And if that's the case, then I can say that M sub R times G minus T sub R is going to equal M sub R times A, or A sub R. Okay, I'll have the same accelerations for M sub L, but it's going to be upward. This is positive downward for that one. For the left mass, I'll have T sub L minus M sub L G is going to equal M sub L A sub L. And because they're connected by that cord, A sub R and A sub L are going to be equal. So I'll just make a note of that here. And then for that pulley, okay, we've got a radius of R. And for the pulley, I'm going to say positive is clockwise for that thing. And that's how I indicate it. And so I'll have torques in this case. And the torque is going to be T sub R times R. That'll tend to give it a positive rotation. And T sub L times R that tends to give it a negative rotation. So T sub R times R minus T sub L times R will equal, for this thing, I alpha. So we've got a moment of inertia for that thing, and so we'll be able to work that into this. All right, well, what else can I do here? I may be able to eliminate T sub R minus T sub L from these equations. I'll have to combine these two somehow to be able to get that to work. And then I'll have it in this equation as well. But there's one other relation that I can use, and that is that for a point on the rim of this pulley, or on the cord that's on this thing, its acceleration will equal alpha times the radius. And so that'll actually be the acceleration for T sub R as well, and the acceleration for T sub L upward. And so I'll just call these A, but the acceleration will equal alpha times capital R. And so now using this, I don't need to know T sub L and T sub R individually. I'll be able to work around this thing. I'm going to call this equation 1, this equation 2, and this equation 3. So let's see what I get out of here. Actually, I'll start with equation 3, I think, and say that T sub R minus T sub L, I'm factoring the left side, times R is going to equal the moment of inertia. Alpha itself is going to be A over R. So I'll have that. And then let's see. Need to work with two. I'm going to add equations 2 and or 1 and 2 together. Let's see. Or T sub L minus T sub R. Actually, yeah, I'll just go and add those two together. I'll get T sub L minus T sub R minus, and I'm just grouping those together, minus M sub L G plus M sub R G is going to equal, let's see, the A's are just going to be A sub R and A sub L are just equal to A. So on the right side, I'll have M sub R plus M sub L times A. So that's what I have eliminated so far. On this equation here, if I divide both sides by R, this equation would become T sub R minus T sub L equals I times the acceleration over R squared. Now, if I add these two equations together, this T sub L will add to the minus T sub L and give me 0. This T sub R will add to the minus, or this minus T sub R will add to that, and I've eliminated the tensions from the equation. And what I'll have left on the left side is just minus M sub L G plus M sub R, or M sub R G minus M sub L G. So I added those two together. Sometimes you have to monkey around to try and eliminate things, and that's the case here. So I'll have that. And then on the right side, I'll have, actually, I'm going to write it as I divided by R squared times A plus M sub R plus M sub L times A. Yeah, I think this will work. Okay, the acceleration ends up being, I over R squared. If you look at that, this thing here, it actually ends up being 1/2 R squared, or excuse me, the R squareds divide out and I get 1/2 M for the rotational inertia divided by the radius squared. I better write that down. 1/2 mr squared I over R squared is equal to this. And it's just 1/2 M. So that's what I have here. And if I factor this, I've got A's in both terms on the right side. I'll have 1/2 of the total mass of that thing plus M sub R plus M sub L. And that will equal, here I'm going to factor the G out of this, MR minus ML times G. This is actually the difference in weights. That's what's actually driving this thing. And the acceleration will equal m sub r minus m sub l times G divided by 1/2 capital M plus m sub r plus m sub l. And that's the acceleration. Now, it's different from the Atwood's machine lab, and the only difference is that we have that 1/2 capital M, 1/2 of the mass of the pulley that's added on to there. If the mass of the pulley happens to be 0, we have an expression that's identical to the Atwood's machine lab. In the Atwood's machine lab, we always assumed that T sub r and T sub l were the same. And if you have a frictionless pulley, that happens to be the case. But here, we couldn't make that assumption. And so I had to eliminate the two tensions as a pair. And I was able to do that with the stuff that I have here. So a more challenging problem here. Here's a similar problem, but not an Atwood's machine. We have a 5 kilogram block suspended by a cord of negligible mass. So this is 5.0 kilograms. We'll actually have numbers on this problem. And the cord is wrapped around a drum with a moment of inertia of 0.050 kilogram meter squared and a radius of 6.7 centimeters. The drum is initially locked in place and is then released. Find the angular acceleration of the drum. Okay, well, I'm going to have to do something similar to what I did last time, and that is make a free body diagram for this thing, make a kind of free body diagram for the drum, although on those, we don't treat them as a point particle, we treat them as a round thing. The drum will have a weight that's acting downward, but there's a support force provided by the bearing that it has running through the middle of it that's exactly opposite that. And we're going to ignore friction anywhere in the bearings in there and treat that the same. So maybe I'll just start with the drum this time and make a sketch of what's going on with it. Okay, the drum's got a cord acting downward here, and this would be actually the same tension that's acting on it here is going to be the tension that's supporting that. So I'll just call it T there, but this T is not going to be the same as the T that's supporting it, but it'll be magnitude-wise, it'll be the same. Maybe I should call it T sub D, the tension acting on the drum. Okay, and this has a radius r. And oops, yeah, I don't need that as a vector, but anyway, the torque that's acting here, I forgot to use that symbol, weird tau symbol. The torque is actually going to equal RT sub D, and with positive being clockwise, that will equal the moment of inertia of the drum times its angular acceleration. And so that's as far as I can go right now. Then come over here and make a free body diagram for the hanging mass, and acting downward on it, I'll have m sub 5 times g, and acting upward on it, I'll have the tension that's acting on the mass. T sub m is what I'll call that. For this, I'll let downward be positive because that's the direction it's going to go when you release the drum. So with down being positive, I'll say that m5g minus T sub m is going to equal m5a. Okay, so I've got these two different expressions here. Yeah, they don't look so bad. One thing to simplify is that the tension that's acting downward on the drum has the same magnitude as the tension that's acting upward on the hanging mass. So T sub M equals T sub D, and I'm just going to call it T. And then there's that relation between the angular acceleration of the drum and the linear acceleration of a point on the drum, including a point on the cord that's supporting that thing. And so the acceleration is actually going to equal r times alpha again. And so these links that tie together the rotation and the translational are handy for this stuff. So let's see, with those, I should be able to simplify this quite a bit. First thing I'm going to do is rewrite these equations. So this would be RT is going to equal I alpha. And let's see, here I'll have M5G minus T is equal to M5A, but I'm going to write that as R alpha, M5R alpha. And let's see, if I divide both sides of this equation by R, I'll get T is equal to I divided by R times alpha. And that's still the same equation. I've just moved that R over there. And now if I add this equation to this equation, the tensions will add out. And so I won't have those left to deal with anymore. So I'll get on the left side, I'll just have M5G. It's that hanging weight that's producing all of this. And that will equal M5R alpha plus I divided by capital R times alpha. And now I just have to factor the alpha out of there and divide by this stuff. I'm going to come over here for that. I will have alpha is equal to M5G, which is the accelerating force, that's the weight of that hanging mass, is going to equal M5 times R plus I divided by R. And now it's just a matter of plugging in the numbers and seeing what this might be. It's going to be less than the acceleration due to gravity because I'm dividing by this stuff. So the M5 is 5.0 kilograms times 9.81 meters per second squared divided by 5.0 kilograms times, let's see, what was it? 6.7 centimeters, which is 6.7 times 10 to the minus 2 meters. I just replaced the lowercase c on centimeters with times 10 to the minus 2. Plus, that rotational inertia was 0.050 kilogram meter squared. And I'm dividing by, again, 6.7 times 10 to the minus 2 meters. So that's kind of crowded, but all of that has to happen in the denominator. So with that, I will use the fancy calculator today. And I hope I didn't punch anything in wrong. Let's see. I'm getting an odd, strange, large number here. Let's see. Five times 6.7 times 10 to the minus 2. Actually, that ends up making that pretty small. Let's see. Yeah, I got a large number, like 45 meters per second squared, which doesn't make any sense to me. Let's see, the kilograms divide out. That'll be kilogram meters there. This is kilogram meters. Oh, excuse me. This is the angular acceleration. Yeah, I was just looking at the units and they're coming out per second squared. And that's because that's what angular acceleration is measured in. So this does make sense. It's 45 radians per second squared. All right. I thought I was finding something that would be the acceleration due to gravity, and it's not. So, because I'm not dividing by a mass, I'm multiplying times a mass, or dividing by a mass times a distance. So we're good. That's a reasonable value for that thing. If we then figured out the actual acceleration, the acceleration is r alpha. It should be something less than the acceleration due to gravity. So if I take that and multiply it by that 6.7 times 10 to the minus 2 meters, yeah, I get 3.0 meters per second squared. So you can see that drum having that rotational inertia slows down the acceleration of the mass by quite a bit. It's only about a third of a g. Okay. Thought we were breaking a law of physics there for a minute. Okay. I think this question and the last one are some that I had on tests at one time, like the final test, maybe. And so this will be good practice to do this one. A wheel with a radius of 35 centimeters is turning at 85 RPM. Okay, well, first thing I'm going to do is write that the radius in meters. 35 centimeters equals 0.35 meters. And 85 RPM, I want to get that in radians per second. So I write it rev per minute times 1 minute over 60 seconds times 2 pi radians per revolution. And so anytime you get something in RPM, that's the process you go through to convert it into radians per second. So 85 times 2 divided by 60. And I get about 8.9. And we've only got two significant figures here. Radians per second. Okay, and that is omega. Omega is measured in, that's when you're given RPM, that's what omega is. It's not a convenient unit. Revolutions per minute isn't, but you can convert it easy enough. So centripetal acceleration, Let's see, people have been using an expression like this, but usually centripetal acceleration, that's a subscript, by the way. Some of you were just writing it as AC on your homeworks, but it's V squared over R, but V is equal to R omega, and so I'm using this relation. It's equal to R omega. That's one of the links between rotational and translational motion. That would be squared divided by R, and you'd have R squared omega squared over R, which is just R omega squared. So we don't have to do that intermediate step of figuring out what V is. We can just use this. Centripetal acceleration is R omega squared, which I haven't looked to see if they had that in the way back when we first studied centripetal motion. I think it's too early to introduce this term, but they may have. Anyway, so I can take the 0.35 meters and multiply it by 8.9 radians per second squared. And again, I've mentioned this before, a radian is just a placeholder unit, something to stick on top of the fraction. It doesn't actually have any physical dimensions. So we'll end up with, where 8.9 squared is, it'll be radians squared per second squared times meters, but ends up just being meters per second squared. Oops. Might make you seasick if I do that. And I get 20, only 2 sig figs, so 28 meters per second squared. For that thing. Okay, we're told the wheel has a moment of inertia of 175 kilogram meters squared, and we know its radius. So I for that thing is equal to 175 kilogram meters squared. A brake is pressed on the outer edge of the wheel, exerting a normal force perpendicular to the surface of the wheel, and as a result, causing a frictional force as well. The coefficient of kinetic friction between the brake and the wheel is 0.77. With what force must the brake be pressed against the wheel to stop it in 9.5 seconds? So this pulls in a bunch of stuff from earlier in the quarter. One thing is that a frictional force is equal to mu sub s times the normal force. This is what we're trying to find. In this case, if you imagine the wheel that we have here, we imagine that it's turning in this direction. So that's the direction of omega. And got the radius r that we've been told, so 0.35 meters. But let's just imagine that over here on this side, we exert a force on this thing, some normal force. That will turn into a frictional force tending to slow this wheel down. And the torque that's produced by that will equal the radius of the wheel. It says it's exerted normal perpendicular to the surface, so it would be the radius of the wheel times the frictional force. This is, whoops, this is kinetic friction, excuse me. R times F sub k, which is R mu sub k times the normal force. And that will give rise to an angular acceleration. Okay. Now, let's see. With what force must the brake be pressed against the wheel to stop it in 9.5 seconds? That's enough information to figure out what alpha is, because we know omega initial is 8.9 radians per second, and alpha will equal delta omega divided by delta t. That's its definition, or d omega dt. But in this case, it'll be omega final minus omega naught. This is 0. Omega naught was the 8.9 radians per second, and the delta t here is 9.5 seconds. A lot of times I would solve all of this stuff in terms of variables, but here let's just figure out alpha by itself. And this would be minus 8.9 radians per second divided by 9.5 seconds. Or 0.94 with a minus sign. 0.94. Let's see. Radians per second squared. Radians per second over seconds are radians per second squared. So we've got a negative angular acceleration. Actually, I should have expressed that in some way here. A torque applied in a way that it will cause something, or negative angular acceleration would actually be negative. So this torque acting on that thing, N cross R, should actually be a negative torque. And so we'd have minus signs all the way along here. And we've got a negative angular acceleration. So the normal force is going to equal the rotational inertia times that negative angular acceleration, 0.94 radians per second squared, divided by, let's see, r times mu sub k, but I'm bringing the minus sign over to that side. And now we can just plug in all the numbers. I was 175 kilogram meters squared, and then the minus 0.94 radians per second squared. Not a real large angular acceleration here, but if this was a flywheel, say for sharpening something or something like that, you're not going to want to exert a lot of force on it because you might chip the wheel, which would ruin it. You might just gradually bring it to a stop. And then on the bottom, we've got minus the radius, 0.35 meters. And the mu sub k was 0.77. So unit-wise, on top, we've got kilogram meter squared per second squared. I'm dividing by meters. That's the only unit I've got on the bottom. So it'll end up being kilogram meters per second squared, and that's newtons. So the normal force, which I wrote with a capital N, and I usually use a lowercase n for those, but I wasn't thinking here. Anyway, that's normal force. It's not a Newton. And it's actually a relatively large force. I get about 610. This I'm going to write out as newtons. And is that normal force? So That's relatively large. So they must have some confidence in their grinding wheel or whatever it happens to have. Maybe it's not a grinding wheel, maybe it's a solid metal wheel. Anyway, that's what the normal force ends up being. So monkeying around with a bunch of these different equations. I haven't used this question on a test again because it pulled too many things together and was just too hard to do when we hadn't done many problems like that. But it's instructive to see how you might do that. Okay, and then here we've got one. A flywheel completes 40 revolutions as it slows from an angular speed of 1.5 radians per second to a complete stop. Assuming constant acceleration, how long did it take to complete the 40 revolutions? Well, we've got a bunch of different choices for equations for actually solving this thing, but really it's going to be the equations for something with constant angular acceleration, and they look like this. There will be something like theta equals theta naught plus omega naught t plus 1/2 alpha t squared, or let's see, omega equals omega naught plus alpha t. Now, we don't know how long it's going to take to stop, and we accept that's what they're asking here, and we don't know what the angular acceleration is. What we do know is how many revolutions it takes to slow the thing down to a complete stop. So we might do something that involves the theta and theta naught. We could think of theta naught as 0 if we want to, and the theta final as 40 revolutions times 2 pi radians per revolution. So it'd be 80 pi radians. And then we might be able to, actually, we could solve for alpha, and then solve this thing for the time. Actually, no, we don't know the time. But there's another equation, which is omega squared minus omega naught squared equals 2 times alpha times delta theta. And we can use this equation to solve for alpha, and then this equation to figure out how long it'll take to stop. So let's go ahead and do that. Omega here is going to be 0. That's the final angular velocity. And so alpha will equal minus omega naught squared over 2 delta theta. Now, 40 revolutions is like delta theta, except it's not measured in nice units. 40 revolutions. If I multiply it, though, by 2 pi radians per revolution, then I get 80 pi radians. And so that's what delta theta happens to be. So plugging in numbers here, it was 1.5 radians per second for starters. So we'll have minus 1.5 radians per second squared divided by 2 times 80 pi radians. And when I'm done with this, I'll have, let's see, top I've got radians squared per second squared. If I divide that by radians, I'll have radians per second squared, which is the usual unit for angular acceleration. So let's see. And I get, let's see, we can only keep 2 sig figs, so I'm going to assume these 40 revolutions were exact. Otherwise, we're down to just one significant figure, and those are never very interesting. But I would get 4.5, whoops, with a minus sign, 4.5 times 10 to the minus third radians per second squared. So that was the angular acceleration. Now to figure out how long that took, I'll use this equation. And omega equals 0 at the end is equal to omega naught plus alpha t. T will equal minus omega naught over alpha t, which is minus 1.5 radians per second divided by, whoops, just divided by alpha. Excuse me. Did you catch that? Let's see. Yeah, kick that across, divide by alpha, divided by minus 4.5 times 10 to the minus third radians per second squared. And the units will come out seconds. So I get 335 seconds. So a long time. Let's see, which would actually round to 2 significant figures. That'd be 340 seconds. So that's how long it takes to stop, which is almost 6 minutes. It's 5 2/3 minutes. The flywheel is a uniform cylinder of radius 0.550 meters and a mass of 66.5 kilograms. So this thing's pretty hefty, whatever it happens to be. What is its moment of inertia? Okay, we'll have to calculate that. And for that, all we've dealt with so far is solid cylinders, uniform cylinders. So it's I equal 1/2 mr squared. Those are the things most common. Let's see, 1/2 times 66.5 kilograms times 0.550 meters squared. So I think I punched those in right. Yep, looks good. I actually get 1.0. No, 10.0. Yeah, I'll have to write it as 1.0 times 10 to the first to show the 2 sig figs. And that would be kilogram meters squared. And then finally, what torque was acting on the flywheel to stop it as described in part A? Well, in part A, we figured out the angular acceleration. The torque is equal to I alpha. And we've got the moment of inertia. We've got the angular acceleration. So 1.0 times 10 to the first kilogram meter squared times minus 4.5 times 10 to the minus third radians per second squared. And remember, the radian is just a placeholder unit. This one's going to look a little bit weird. However, when I just multiply these things together, this is actually 10, or I'd get minus 4.5 times 10 to the minus 2. To the minus 2. Okay, unit-wise, we will have kilogram meter squared per second squared which is a joule. But another way of expressing a joule, if I pull out one of these M's and stick it on the end, I'll have a kilogram meter per second squared, which is a Newton times that meter. And that's the way that we write torques, is as Newton meters. But you should always check to make sure before you start that monkeying it, make sure you've got kilogram meter squared per second squared, which you can then write as a Newton meter. And we have a minus sign because we got a negative angular acceleration slowing that thing down. So, but the magnitude would just be 4.5 times 10 to the minus 2 Newton meters. So there are a series of examples just messing around with basically Newton's second law for rotations, except I don't think Newton dealt with analyzing rotations as far as I know. But anyway, quite a few problems there, and they work out. Do you have any questions on that? Okay, I did start recording somewhere way back. So I'm going to stop the share and I can end the meeting, and I'll be posting the time for the review sessions as soon as I hear from the students that had very difficult times to meet. So I'll do that.